So in this part, our aim is to understand the graph of rational functions and some related transformations. So before going into rational function directly, we should start by learning the graph of reciprocal function. So the basic reciprocal function we should start from is the graph of fx is equal to 1 by x. So how we draw it? So I have the function fx, and this is 1 by x. You know that the function fx, which is defined as 1 by x here, is the reciprocal of the function fx is equal to x, or gx is equal to x, or maybe we can say directly y is equal to x. So this is a rectangular hyperbola, you know, but let us try to understand in a different perspective. So for that, let's draw the graph of y is equal to x, and we will try to understand the reciprocal nature of y is equal to x to draw the graph of fx is equal to 1 by x. So the graph of y is equal to x is a line which is passing through origin and inclined at 45 degrees with the x-axis. So it will pass through each corner of the grid, because it should pass through 1 1, then it should pass through 2 2, then 3 3, and so on. Similarly here, and this is the graph of I have y is equal to x. Now to draw the graph of the reciprocal of any function, we have to just inverse the nature of the given function. The meaning inverse means, it doesn't mean that the inverse function is the reciprocal in nature. So you can see that if I have the function fx is equal to 1 by x to draw from y is equal to x, you can see that when x equals to 1, the function value for this is also 1. It means at 1, the reciprocal value will also achieve the same 1. And at minus 1 also it will give you the same. But what will happen if I substitute 0 in this? You can see that when I substitute 0, the function is not defined. It means whenever you are seeing the denominator is 0 anywhere in the rational, it means that there must be an asymptote. It means here the y-axis is the asymptote for the 1 by x function. So let's draw it just for the sake of understanding where is the asymptote. So this is the asymptote I have drawn. This is x equals to 0. Now you can see from 0 to 1, whatever value you substitute here in this place, the function fx will give you the value higher than 1. How can we know that? If I'm substituting, let's say 0.5 or 1 by 2, the value of the function will be 2. So for any number 0 to 1, the value of the function is higher than 1. It means between this interval 0 to 1, the graph of the function should be above 1, means higher than 1. At 0, it is infinitely high, so it should start decreasing, because from 0 to 1 it's still increasing there. So it should start decreasing but remaining above the y is equal to 1 line. So it will decrease like this, and at 1 it should hit this one, and again after 1, whatever you substitute there, that will give you the value lesser than 1. So after 1 it will start decreasing, because still the function fx is, the y is equal to x is increasing, so the reciprocal nature is still decreasing. We have to decrease the graph. But when we go for higher x tends to infinity, that value ceases to be 0. So now there is again one horizontal asymptote for this function, and that is the x-axis. So this is this part or this branch, you know, and similarly we have to draw in this branch. So we have drawn these two branches of the function in the two opposite quadrants, or this 1 by x. So what is the important thing I want to convey here is, you can see that this entire graph is symmetrical about the line y is equal to x. And why so? because when you find the inverse of this function fx, fx is 1 by x, the inverse is still 1 by x. So when a function and its inverse are same, then the graph itself will be symmetrical about the y is equal to x, because here you can see that the function is fx 1 by x, the inverse is still 1 by x. So f of fx is x. If I have any such kind of nature, then what we can say, then fx graph is symmetric about y is equal to x line. It means the one half which is above the y is equal to x line, it's symmetrical to the bottom half in the both of the quadrants. You can see that. All right, so this is the way we can understand by drawing the graph of y is equal to x, and how we can draw the graph of 1 by x from there. Let's try to understand how we can draw the graph of 1 by x square by just observing the graph of x square as well. So before that, let me try to give you one more example of such kind. Let's try to draw the graph of 1 by mod x. And why I'm saying that to draw here only, there's a reason. Because you know that, okay, let me just first write, I have y is equal to mod x, and I want to draw the graph of fx is equal to 1 by mod x. So if I know the graph of y is equal to mod x, it is like that. In this quadrant as well as in this quadrant. And once we know this graph, I can safely draw the graph of 1 by x, as we are replicating the previous function, because you can see that it's also y is equal to x in the first quadrant and in the third quadrant. But here you can see that in the first quadrant is the y is equal to x, but in the second quadrant is the y is equal to negative x. But it doesn't matter, because now I can say that this part we can simply replicate like this, and this part we are going to do the similar process. Or you can also see that once I draw the graph of 1 by x, once I draw the graph of, not this thing, once I draw the graph of y is equal to 1 by x, I can take the modulus, and we take the modulus, it means that we are taking the image of the graph below the x-axis, which is lying in the third quadrant. So we are taking the image of it on the second quadrant, or the other side of the x-axis. You know how to draw the graph of this thing. Or you can also see that if this is y is equal to 1 by x, I can also think that this is not, I'm taking the mod of the entire function, I'm taking the mod of x only, means taking the mod from inside. So in this way you can also see that I'm taking the image of this branch of the function, this side. So I've taken the image, and I'm actually ignoring which is already left to the y-axis. So all the other techniques we can apply, all these techniques we can apply to draw the graph of 1 by mod x from y is equal to mod x, or from the scratch. All right, now we go to draw the graph of y is equal to, or the fx is equal to 1 by x square. How do we draw it? So for that, let's draw the graph of first x square. So x square graph, let me just take, oh no, just take the graph of x square as it is, as we have drawn previously. So this is the graph of y is equal to x square, and I want to draw the graph of reciprocal of it. So we have to reciprocate the behavior in the interval. So how do we reciprocate? You can see that at x equals to 0, this value is not defined. It means again we have the asymptote at x equal to 0, that is the y-axis. So this is our asymptote I have, and you can see this graph is increasing in this interval. From here to here is increasing. So the reciprocal graph should decrease from infinity and go down, because when we go for x tends to infinity, then this is ceasing towards 0. It means the graph on this part will look like, let's say this value is 1 at 1, because when we take x equals to 1, either it's a reciprocal or plane, the x square will also give you the value 1, and 1 by x square will also give you the value 1. So these two graphs, the y is equal to x square and y is equal to 1 by x square, will meet each other at 1, 1. Similarly, this branch we can also draw at minus 1, 1, and this is also symmetrical, you can see, and this is a graph of y is equal to 1 by x square. So this green graph, what you can see here and here, is the graph, and this graph we have drawn just for the sake of our help. So this graph y is equal to x square we have drawn just for the help. All right, so in this way we have drawn the graph of 1 by x square. Let's try to draw the graph of 1 by x cube. So for that I need to draw the graph of x cubed first. So you know that the graph of, so I am intending to draw the graph of 1 by x cubed, and for that I need to take the help from x cube actually. So x cube graph, you know, this is, let's say this is 1, 1, and it should go like this, and it will go till infinity. Similarly here it will go like this. This is schematic diagram. Now I want to draw the graph of 1 by x cube. How we can do it? So see here, from 0 to 1 the graph is increasing, or by the way 0 to infinity it's always increasing. So this time 0 to infinity the 1 by x cube should be decreasing, but at 0 again you can see that there is an asymptote because the 1 by x cube is not defined. So this is again x equal to 0 is an asymptote, so to start decreasing, and at x equals to 1 again they should meet each other. So it should look like this in this part, like this. And similarly here for any x negative value, the function value 1 by x cube is always negative. This will look like this. Don't get confused by the graph of 1 by x, because it's a different from that. You can compare by just plugging the value, because for 1 by x, when you take x equals to half, that will give you 2. So for x equals to half, this 1 by x will give you the value 2, but 1 by x cubed value will give you 8. So it means at half the 1 by x will be below the 1 by x cubed actually. So it is still higher at half than 1 by x. So but the diagram when we draw without any comparison of any 1 by x of such other graph, we can draw the graph freely until it is not making any confusion. So this is the graph of 1 by x cube we drew. Now let's try to draw the graph of 1 by x square plus 1, and for that we will take the help from x square plus 1. And by the way, one more thing I wanted to convey, you can see that when I draw the graph of x square and the reciprocal of it, the graph will remain always above the x-axis because it's a positive quantity. And when I draw the graph of x cube or the reciprocal, the graph will lie in these two quadrants. So what will happen if I draw the graph of any such pure quadratic reciprocal or pure even power reciprocal? It means suppose I want to draw the graph of, suppose you want to draw the graph of, suppose you want to draw the graph of 1 by x to the power 4. So 1 by x to the power 4 will be the reciprocal of x to the power 4, and x to the power 4 graph is a little bit flatter, but it's still in the behavior of x square. So again 1 by x to the power 4 will look like similar this kind of graph. And suppose you want to draw the graph of 1 by x to the power 5, it will look like the graph we drew for 1 by x cube. So whenever I have the even power in the denominator, the pure even, there is no such linear or any other constant term. So suppose I have 1 by x to the power 2k, I have the plot of such kind. And whenever I have the 1 by x to the power 2k plus 1, then the 1 by x to the power odd, the graph will be such kind, means the green part. In this way, we can understand that how we can draw the graph of any reciprocal of pure quadratic or any pure degree or any power. Now we try to draw the graph of x squared plus 1 reciprocal. So again, I'm taking the axis and I have this axis here, and I want to draw the graph of 1 by 1 plus x squared. And for that, I'm taking the help from 1 plus x squared. You know, the graph of 1 plus x squared is a graph open upward parabola which is shifted 1 unit above the x-axis. So this is the graph of x squared plus 1. And you can notice that there is no such point at which this denominator is going to be 0. So there is no such asymptote we have. So now we can think what will happen. When x equals to 0, in both of the functions, the function 1 plus x squared or its reciprocal, the value is 1. So before x less than 0, means before x is equal to 0, means for x less than 0, this function is decreasing function. It means the reciprocal should be increasing function. So it should increase like that, and at 0 it will meet the same value, because at 0 they will have the same value, and it will replicate the same graph what we drew in this side. And again, at x tends to infinity, it is going to be 0. That's why I have the horizontal asymptote for them, that is y is equal to 0. And it will not come down because always it will be above the x-axis, because it gives only positive quantity. So this is the graph of 1 by 1 plus x squared. How do we draw the graph of now 1 by 1 plus x cubed? So for that, I need to take the help from 1 plus x cubed. So for that, I'm drawing first the graph of 1 plus x cubed. So I have this y is equal to 1 plus x cubed. And here it's a little bit important to understand, because we have to be very careful in drawing this thing, unlike we did carelessly for 1 plus x squared. So here I have to shift the graph of x cube 1 unit above. So this will be the graph of x cube, and of course this value will be -1, and so on, and this point is 0, 1. Now I want to draw the graph of 1 by 1 plus x cube. You can see that when x equals to 0, they will meet each other, because at 0 they have the same value, that is 1. But at x equals to -1, what we have here for this x cube plus 1 graph, this value in denominator will become 0. And when denominator will become 0, there must be an asymptote. So let me draw the asymptote first. So this x equals to -1 will serve as an asymptote for 1 by 1 plus x cubed. And now what will happen? We have to draw the graph. So you can see that from here, from -infinity to this part, the graph is still increasing. So we have to draw the graph increasing, but we have to draw left to the asymptote or right to the asymptote differently. So from -1 to 0, it's still increasing, so it should decrease now, and it should decrease like that, and at 0 they will meet each other, so it should decrease and it should come to meet this point, and again it's increasing, so it should still decrease, and at extends to infinity it should go to meet the x-axis at infinity. So in this way we have to draw it. Let's draw it to this side. I have to draw like this. It should come like this, and again it will go like this. So this is the part we drew for when x greater than -1. What will happen for this side? So notice that this was the entire graph from there, so it is still increasing there, so again the graph should decrease. But you can notice that whenever I'm taking any value lesser than -1, this is still negative quantity. This quantity is negative, so the entire quantity is negative. If you substitute x equals to -2, this will give you 1 minus 8, and so it is negative quantity. Here after -1 it will be positive, that's why it is above the x-axis. So here I have to be negative, so it's decreasing, so it should start it is increasing. The x cube plus 1 is increasing, so the 1 by 1 plus x cube should be decreasing. You start from very far from x-axis, and it will go like this, and again it will try to meet this x equals to -1 at negative infinity. So this is the way we have to understand. I'm not saying that this is the exact graph. We are only drawing the schematic graph just closer to accurate, so that whatever the qualitative analysis we have to do from the graph, we can do. Alright, now let's try to draw a very interesting one. What I'm saying, interesting one. Can we also use this kind of technique to draw the graph of 1 by log x? Let's try. So intention is to understand how we can draw the graph of 1 by ln x, and I have already the graph of ln x. So let's first draw the graph of ln x. So the graph will go like that, and this point is 1, 0. And to draw the graph of reciprocal, you can see that at 1 there is denominator 0. It means at 1 there must be an asymptote. Let me draw this asymptote first here. And now what will happen? You can see that at 0 the function is not defined. It's very interesting. At 0 the function is not defined. But as soon as you substitute a little bit ahead of 0, let's say 0.00001 something, it starts showing some value. Because at exact 0 the log x function is not defined. But that is why this graph, the log x, we have drawn without just touching the y-axis, because at 0 there is no such value. The same way it will start just after 0, but some value will be there. Between 0 and 1, you know that the log x is always negative quantity. Therefore 1 by log x will be also negative. So this graph is increasing, so the reciprocal should be decreasing, but it should be below the x-axis only. So we have to draw like this. It will come exactly, not just touching 0 anywhere. There is some gap here. It will come and it will go up to -infinity at 1. Now after 1, what will happen? The graph will give you the value always positive, so it should show above the x-axis. So here it is increasing again after 1, so it should start decreasing from infinity and will decrease like this. So this way we can draw the graph of 1 by ln x. Let's try one more interesting one. So this time I want you to understand how we can draw the graph of 1 by e to the power x square. It means I have y is equal to e to the power x square first, and my intention is to draw the graph of 1 by e to the power x square. So I'm going to give you the idea how we use the reciprocal concept by the way, it can be also seen that it is nothing but e to the power minus x square. So if you know how to draw the graph of e to the power x square, and I have already taught in the previous videos that if we have the minus of function, sorry, f of minus x from fx, how we draw the graph. The graph will flip in horizontal axis or y-axis, you know that. So for that, let me just do that for reciprocal part or reciprocal way. So for this e to the power x square, how the graph will look like. You know that, what is the graph of e to the power x first? So this is the graph of e to the power x I'm drawing, and my intention is to first draw the graph of e to the power x square by doing some analysis, visual analysis for e to the power x, and then we draw the reciprocal. So I have y is equal to e to the power x, this graph. Now you see, there are no such major changes. There will be major changes. If you see exponentially, it's a very high number, just a square of it. But graphically, if you are drawing this thing, the behavior or the shape of the graph is not that much change if you're not comparing. Why so? Because when we're substituting x equal to 0 there, the value is 1, still there's a 1. So e to the power x square should also go from 0, 1, go through 0, 1 rather. And you can see now, whatever value you take a negative side, now it is not in consideration. Because suppose I'm putting x equals to 1 there, it will act as 1. So means x square will act as 1 and e to the power 1. So for x equals to 1, let me just show you. This is y is equal to, here I'm talking, is 1 only. But x equals to minus 1, it will be the same. It means whatever you see this part, it is not anymore in consideration. Because for every value, if you go ahead or back, it has the same height because of x square. So can we not replicate the same graph here? And I can say that this is the graph of e to the power x square now. Because there is no such major changes, because the only thing is x square value will be higher than the x value. But the graph is a little bit same. Now, if this is the graph of e to the power x square, I have to draw the graph of reciprocal of it. So what we can say that, let me just take this x-axis a little bit down so that I can draw the graph of it. So for this part, you can see that the graph is decreasing, means the e to the power x square graph is decreasing. I'm doing the reciprocal of it. So our graph should increase. So it should increase from the x-axis, and at 0, they will give you the same value. So it will again meet this 0, 1 and again do the symmetry. And you can also use the even function concept, because it's the even function, because f of minus x is this fx. So once we draw the graph right to the y-axis, we can reflect it to the left or vice versa. So in this way, we can draw the reciprocal of that. And you can also understand, if I want to draw the e to the power minus x square, what will happen. All right. So these are some reciprocal graphs. Let's do one question and then we will go for the rational. The question is, for what value of k, the equation fx is equal to k has no roots, where fx is 1 by x minus 1. So let's try to draw this, solve this whole question graphically. So my intention is to first draw the graph of y is equal to x minus 1, and then we draw the graph of its reciprocal, and then we try to think from where to where k is not going to give any solution. So this is a pure, not pure, this is a quadratic actually. So you can see this quadratic has two roots, the 0 and 1, and the x square coefficient is positive. So the graph of x minus x, x into x minus 1 should be the open up and passing through 0 and 1. So let's say this is 0 and this point is 1, and I'm drawing the graph of this x square plus 1. Now at the same time, I need to find out this value. So this is 0 and this is 1, And this value we can find out as exactly, let's say this is y, so I have y at half. Y at half because the half is the midpoint of 0 and 1, so the depth or the height of any parabola or the vertex can be decided at the minus b by 2a. So half will give you the value of the depth. So at x equals to half, there's a half times half minus 1, so they'll give you minus 1 by 4. So this point is our half comma minus 1 by 4. Now you notice to draw the graph of its reciprocal here, I first need the asymptote because it is hitting the x-axis at 2 points, 0 and 1. And so at 0 and 1, the denominator here becomes 0. So this is the first asymptote I'm drawing. This is itself the y-axis. And this is the second asymptote at x equals to 1. So these are the two asymptotes we have drawn, x equals to 1 and x equals to 0. Now you can see the function what we are intended to draw is decreasing from minus infinity till 0. It means our function should increase from minus infinity to 0. And here also after 1 it is increasing, so that should decrease. It's not difficult. For this part, we can simply take it like this and draw it. It's an increasing function. And we don't care where they are intersecting because I don't think it is important for our question. If we need to know, we have to solve these two and see that for what value they are going to intersect each other. Here also is a increasing, so I have to make a decreasing part like this, and this is the graph we draw for the upper part of the x-axis. For the lower part, you can see what is happening. At 1 by 2, the value of the y function, the original function, is minus 1 by 4. So what will happen? At 1 by 2, now the reciprocal will give you the value minus 4. Is a minus 1 by 4, so reciprocal will be minus 4. So it will start moving from somewhere. Let me just extend this y-axis, and also this asymptote, because the graph what we are drawing in this 0 to 1 portion will always lie between two parallel lines, the x equal to 0 and x equal to 1, because after 1 there's other graph which is above the x-axis, and also before 0 there's other graph, so we cannot draw the graphs, remaining graph inside that. Also you can see from 0 to 1 this portion is decreasing, so our portion what we have to draw should increase, but where till it will increase? At minus 4 only. Let's say this point is minus 4, that is 0 comma minus 4 here, and so till here my graph should increase because of the reciprocal is decreasing, and after that it should decrease again because reciprocal is increasing. And so this all green parts what we can see combinedly will give you the graph of 1 by x into x minus 1. Now the question is asking that what are the values of k so that there is no roots. So y is equal to k is a line what we can draw from here, starting from here and going up to here. So whatever the line you draw, y is equal to k in this part, there is no such solution will reflect other than this part. If you draw any line, it will be intersected by the curve, the green curve, and we have the solution. It means the k value should lie from minus 4 to 0. Minus 4 you cannot include, otherwise there will be one solution, and 0 you can include because it will never touch because it is the asymptote. So k is lying from minus 4 to 0. Even if you take k is equal to 0, there will be no solution. All right. So in this way, we can draw the graph of 1 by x into x minus 1 and solve this question. Now we understand how do we draw the graph of any rational function of such kind in which the numerator and denominator are linear. So for that, I have taken an example, and our aim is to draw the graph of 2x plus 3 by 3x plus 1. So first of all, we will check the vertical asymptote, and for the vertical asymptote, I'm saying the denominators cannot be 0. So vertical asymp, I'm saying. So at x equals to minus 1 by 3, you can see the denominator is 0. Therefore, this is the vertical asymptote. And we also find the horizontal asymptote. I will show you how, but let me just give you some calculus way. So horizontal asymptote will be given by just take the limit of this function. So limit x approaches infinity, 2x plus 3 by 3x plus 1 is, if you know the limit concept, you know this is a linear by linear, and if the degree are same, the for x tends to infinity, the value of the limit is the ratio of the leading coefficients of x. So this is 2 by 3. So we know the vertical asymptote is minus 1 by 3, the horizontal asymptote is 2 by 3, and this minus 1 by 3 is coming from just seeing the denominator is going to be 0 at that point, and this we have to evaluate the limit. So in this way, we got the vertical and horizontal asymptote, and we try to draw the diagram. So for that, I need axis again, and here we will draw it. But before that, let's try to decode it and understand this whole scenario by taking the shift and other concepts. So suppose you have fx 2x plus 3 and by 3x plus 1. What I mean to say is that I'm not trying to draw the graph of this entire complicated thing. I'm just looking at one rational function, the reciprocal function, and trying to shift it, and the process of which the asymptote will also help us. So for that, I'm going to write this 3x plus 1 there. So in fact, in principle, I'm dividing the numerator with the denominator, but the technique we can do in this way, avoiding the long division. So here 3x plus 1 I'm writing on the top, but I have to make it 2x plus 3, so I'm just multiplying 2 by 3 so that I can get 3 and 3 get cancelled, and I'll get 2x. But extra I got 2 by 3, and the 3 was already there, so I'm adding 3 just to show it 3 here, and I'm subtracting 2 by 3 because it's not there. And denominator I have already 3x plus 1. So what will happen next is I can separate it, so I will get 2 by 3 at the first place, and here I'm getting 3 to the 9 plus 9 minus 2 7, so I believe it's a 7 by 3 and 1 by 3x plus 1. Now you see that what is happening here. Let's try. Can you not see this way that this original graph was 1 by x, and you have given some transformations in each step to get this whole scenario? How can we understand this thing? Let's do one more calculation and we'll get the whole idea. So for that, I can see this is 2 by 3, not difficult. I can taking this 3 out, so I'll get 7 by 9 and 1 by x plus 1 by 3. So don't you think that I am just first taking 1 by x, I'm shifting this 1 by x, 1 by 3 unit left, again I'm scaling this by 7 by 9, and whatever scaled function will come, I'm shifting it 2 by 3 unit above the x-axis. And in this whole process, our asymptote will also work. So let's first draw the asymptote. So I have minus 1 by 3, which is I'm taking here. So let me take the straight line. Let's say this is minus 1 by 3 I'm taking here. And also 2 by 3. I'm taking a little bit ahead, which is here. So these are the horizontal and vertical asymptotes we have. So this is y is equal to 2 by 3, which is a horizontal asymptote. This is x equals to minus 1 by 3, this is a vertical asymptote. And I have to draw the graph of this. So you see this graph is 1 by x graph is shifted 1 by 3 unit left. So and the 7 by 9 is a scale factor, and you can see this much not giving you some significance, some significant effect. So I can safely draw the graph of 1 by x, pretending that I'm drawing the graph of 1 by x plus 3 by assuming that x equals to minus 1 by 3 is our asymptote. So in this way, we do this part. Also, we take care of where it is intersecting the y-axis. So for that, don't put x0 there, it's a little bit complicated, put 0 there. So what is f0? f0 is 3 by 1, that is 3. So this point I will mark 0, 3. And this is our graph, this part. And again, you can see just opposite to it, there's this quadrant, and we have to see that where it is intersecting the x-axis. So for that, I have to solve this. That is 2x plus 3 is equal to 0, because this whole thing should be 0 for getting the point on the x-axis. So x equals to minus 3 by 2. So x equals to minus 3 by 2 is somewhere here. And the graph will come down like this. And this is the entire graph we have drawn. You notice that this 7 by 9 is not getting any effect. Means, so to speak, when we are drawing this graph, not up to that much scale, or we are not comparing the graph, this fx graph with 1 by x plus 3. Of course, this will give you some effect, but we are not showing this effect because it's not shown also until we are drawing exactly. So we have drawn this schematically without just considering the 7 by 9, because 7 by 9 is responsible for the vertical stretch, and vertical stretch can be shown effectively by hand only if the graph is pinned on the x-axis. But this 1 by x graph is never pinned on the x-axis, so the only scale factor happens in the open space where we can just freely draw the graph. All right. Now, this is the way I think that's effective to draw the graph of any rational function. One thing you can notice that when this graph shifted from this place, from which place? From this place, it was originally here 1 by x, and you did some transformation. So when the graph was there at 1 by x, it was already symmetrical about y is equal to x. But this time when we did some transformation, the shifting happened and the y is equal to x symmetry will lose. All right. Now we do this question. This question I think you have encountered many times if you're doing the function and it's inverse. So the question is, the fx is ax plus b divided by cx plus d, and the f of fx is equal to x. For this, what is the condition on a, b, c, d? Find the condition for which f of x is equal to x. So there is an analytical way, just by substituting the f of fx and comparing the right hand side and left hand side with the coefficients and get the value. But I want to make you understand how we can see the whole scenario or whole thing by graphically. So graphically we can just understand why it is happening, and it's very fun and interesting. So here you can see that the f of fx is x is giving you the idea is a f of x is f equal to f of f inverse x. So it means that the function and its inverse is the same thing. It means if you find the inverse, you get the function back. So what is the meaning of that? it means that graphically the function graph is itself the mirror image along the y is equal to x line. It means y around the y is equal to x line, the lower part is the replica of the higher part and vice versa, as we discussed for 1 by x graph. So let's try to convince ourselves the whole scenario in this graphical journey. So for that, again, I have to draw this graph, and I'm not drawing this graph complicatedly. I'm trying to draw it very easily. Let's try. So I have fx is equal to ax plus b by cx plus d, and I can write it here, cx plus d, the same process I'm doing here, and for that I need a here, so I'm dividing by c and multiplying by a, so I get ax, but extra I get b over there and minus ad by c, and this whole divided by cx plus d. Now I can separate it, so it will be a by c and plus b minus ad by c, and from there I can take c common, so x plus d by c. Now what I'm doing there is I'm considering this whole thing together, that is b minus, what I'm doing there, b minus ad by c divided by c, I'm taking as one constant k, because in the previous example you notice that is not going to affect our whole transformation process because the graph is not pinned on the x-axis. So it will give you this vertical stretch or maybe the vertical compression. It depends upon what is the value of b, a, and all this constant. So it will give you the vertical stretch or shrink, but it is not visible there because the graph is not pinned on the x-axis. So I'm taking this k there just to be there as the part of this whole expression, but not that much significant. So I have this function now, and I had already the graph of 1 by x, and I'm shifting that graph or doing some transformation step by step to achieve the graph of fx. So let's try. I have 1 by x graph here. This part only I'm drawing. This part is not that much important to understand the concept, but let's see it. You notice that the graph is shifted d by c unit just to get the asymptote, minus d by c means on the left hand side, and again a by c unit up. In this whole process, what is happening? Let's see. So if I shift this graph, minus d by c unit left, so let's draw this line as x equals to minus d by c. So x equals to minus d by c, this graph shifted there. And also the horizontal asymptote will be a by c. If you see that here, when x tends to infinity, the a by c. So whatever comes here will be the horizontal asymptote. You can see in the previous example also, whatever came here, it will be the vertical horizontal asymptote, and this x equals to minus 1 by 3 is the vertical asymptote. So I have a by c as the horizontal asymptote. So this I'm drawing vertically there, a by c, and it's minus d by c. It means our graph will look like that in this quadrant. But what happened there in this whole process? Do you see that we have disturbed the symmetry of this entire graph along the y is equal to x line? It's not symmetrical anymore. So how do we preserve the symmetry? Why am intended to preserve the symmetry? Because in the entire transformation process, or whatever you do for the function must exhibit the given property of f of fx is equal to x. It means the inverse of this function is itself. And so it should always be symmetrical about the y is equal to x line wherever it goes, whatever transformation you will employ over it. It means what you did, you see that when I'm shifting the graph leftward and I'm shifting the graph up, the graph symmetry disturbed. So to get the symmetry, see that if I just try, suppose you have this original graph and suppose I'm shifting the graph some unit left. To make it symmetrical about the y is equal to x line, I have to shift the graph by the same unit down. Then only it will remain symmetrical, because when you're shifting left, you have to shift down. You're shifting left, you have to shift down. To shifting left, shift down. Then only it will remain symmetrical about y is equal to x. When I'm shifting the graph rightward, I have to shift by the same unit up. Shift left, shift up by the same unit. Then only, because y is equal to x, we have to be symmetrical. So this branch must be symmetrical about this branch. So whatever you shift left or right, you have to shift by the same unit up and down. Then only it will remain symmetrical about y is equal to x. So in this process, what you did, because a by c we don't know, d by c we don't know. So what I did, I shifted leftward by d by c unit. So I have to maintain the symmetry about y is equal to x by shifting it down. It means this a by c must have such feature that it will shift the graph by the same unit down. So I can say that the a by c must be equal to minus d by c. Then only the graph will be preserving its symmetry about y is equal to x. And so a is equal to minus d, or a plus d is equal to 0, as you remember for this kind of functions, for f of fx is equal to x. Alright, so I hope you understood many things here. Whatever I think graphically, I have conveyed to you. All the best, and see you in the next video with some other graphical transformation, perhaps the trigonometrical transformations. Till then, stay math active.